Welcome everyone to our class on DESeq, where we are going to start to take the counts from the pipeline we ran and see what DESeq wants for those type of values. There's a little bit of background we should go through of what came out of the pipeline, what does DESeq want for different things, and that's what we'll cover here today, and actually run DESeq to get normalized log counts that we'll want in the future. Okay, so we're here in class 2023, classes 05, RNalyses, RNAseq, and we've moved into differential expression now, and we're doing DESeq counts, where we're going to cover all the basics of what is the input to DESeq and how does it need to be set up and what sort of things should we consider moving forward with that. And if you are on the web here at long-non-coding-RNAio.teaching/teaching, then we are here in RNAseq analyses on this website. Okay, so let's get started here. I'm going to work from my RStudio. It's the same code that's on GitHub. And we will install our packages here, and we will be installing DESeq, which is going to need this locfit program. So you might want to pause it here, install this and DESeq, and we'll need that for today. Okay, so before we get started, it is always good. We just ran the pipeline here in our RNAseq 00 folder. We ran it in this NF-core RNAseq pipeline, and we have a results folder. And as I sound like a broken record, the first thing to check out is multi-QC here with this multi-QC report. How handy is it that Nextflow did all of this, NF-core did all of this for us. So we have all of this information, and what we noticed here is samples clustered as we would have expected by the type they are, so what fraction of the cell they're in. Here we see clustering together, and then here we see these two being much more similar across experiment accessions or type of RNA than together, and that's very suspicious. And so we went in and looked at the raw data and actually said, well, if this is actually insoluble, then a nuclear gene would not be expressed there, and it was, so we figured out it was total RNA. It's all written out here, and then you can look in your multi-QC report because you'll have the same issue. This sample was simply just mislabeled by ENCODE, and there's nothing we can do about it except for fix it now that we know what is what. And so that's all outlined here, and how you can how we need to now fix our sample sheet. And so with DESeq, it's always good to have a sample sheet. We spent a whole class making the sample sheet, but as you'll see, it's going to be really handy to keep track of information on each sample and then connect it to the values of RNAseq in each condition. So this is just, I guess, a practice in tidyverse. There's nothing we can do. We have to change our sample sheet that we made last time. I'm going to make sure I'm in the right working directory here. And this is the sample sheet we previously made is in our results here. And so if I load that in, I can see we have sample sheet with these 10 observations, but it turns out replicate 1 of total RNA is actually insoluble, and replicate 2 of insoluble is actually replicate 1 of total RNA. So it's good to look at your QC, look at the raw data, and just make sure things make sense. Like if you're comparing nuclear RNA, you can look at the total reads, and your nuclear gene should be higher. And I outlined some genes we looked at to figure that out. So now what we can see is here, we are simply indexing into sample sheet sample name, which is the column we want to change, where it says Homo sapiens HepG2 replicate 1 in condition column. So we're basically saying rows and columns, and specifying one single row and the column in which we want to change. And the which is just taking this as logical trues and falses into ones and zeros and indexing into sample sheet. So if we run that, what we'll see is the condition column has now been replaced with this. So we can see Homo sapiens hep G2, which is total RNA, is actually the insoluble one. I apologize that this is confusing, but it's a good example of how even the most careful people can sometimes have mistakes you have to be aware of. Okay, so we've changed that one. Now I'm just going to change the condition of this cytoplasmic one to total RNA. And I'm using the same strategy here, so I'm not going to go over it. You can pause and look through it, except for I'll point out that here we now need to change the replicate number, because we can see once we've made these changes, there's this is going to be replicate 2 and not replicate 1. And so we need to rewrite the sample name here, and you can watch those change. And then we're making this replicate X here, so we don't rewrite over the name when we change it again. So we'll have 2 names at some point that are the same. And if we select on that name, it's going to change both of them. Again, think of this as a good practice in indexing and tracking samples and being pretty careful about it. So now I'm changing this back to replicate 1, changing Rx back to replicate 2, and then now we need to change the actual replicate column here. So if we look at our samples now, we can see we have replicate 1 as replicate 2, and replicate 1 as replicate 1, replicate. So this has got to be fixed here. And I must not have run one of the corrections. First, to change the name, sample name, replicate back, replicate number, and now we should have everything in order here. So we see we have 2 totals, 2 nuclear, 2 membrane, 2 insolubles, and they are all with the correct replicate number here. Okay, all of that just to make sure we have the right samples. And now we're going to load in the GenCode gene annotations object. There's in previous classes how to download that, especially in the NF Core ChIP-seq pipeline class. Excuse me. So we're going to import that. I already did that because it takes about 5 minutes. So if you want to pause and go there, and really the goal we're going to make is just a list of gene names of link RNAs and mRNAs, and just get their gene ID, which is a long number, and their gene name, which is a little more intuitive. And we're going to save that to load into our environment in the future, so we don't have to keep spending 5 minutes loading that. So now I can make GenCode genes from this the same way we have before, is going in and indexing into type of gene. And you can practice seeing what's in here by just doing these kind of things and maybe add a table to that and see what it is. So we're going to make this gene to symbol G2S object, where we're going to take our ENCODE genes and make it as a data frame and just select these 2 columns out from the whole mess of information in there. And if we now look at G2S, we get this nice table of gene ID and gene name, and we'll save it at the end so we don't have to make that again. Okay, so you can save that to have it written in. And we probably want to save the sample sheet, which we'll do in a minute here. And so now what we are going to get from our pipeline analysis, probably the most important thing we got was the multi-QC and the counts per transcript. So for each gene, we now have the number of counts that were present in that gene, normalized by the total number of reads in the sample, but it's pretty raw. So it's just saying counts over the transcript. And this is what I want to kind of get across in this class, is just thinking about counts versus R log counts, where the counts have been normalized by their variance and how noisy the gene might be. We're going to go into those normalized counts in a minute, but the first thing we get out is Salmon counts. You can think of as a safe, raw set of data to use, and we'll go through what we can do with that. So we're going to load that in. That is in our RNAseq 00, where you ran the pipeline. In our results, we have the Salmon folder here. This is the main thing you'll want for data. And we get all these different quantification schemes here. And we are simply looking for salmon gene counts. You can do this by transcript where every isoform has a value. But for our purposes, we're first just going to compare nuclear cytoplasmic RNAs and see which ones are enriched in which compartment. So we can do that on a gene level here. So we read that in, getting the salmon merged gene counts here. And that is what you want. I highly suggest looking up what salmon does and what its outputs are. And it's in that NF core RNAseq documentation as well. Okay, so let's look at our counts here. We can see that gene ID is a column, and we might want to put that into the meta column or use column to row names just to move gene ID out of the matrix. So the data, just data in the matrix. And now we're going to connect this to our sample sheet where our counts object has now a column with the gene's ID, and our sample sheet also has the sample name for that, for each of these replicates. This is in our sample sheet here with sample ID. And we can now use this sample ID to find the object in counts here. So that's what we're going to do now, is say for counts, subset out only the things that are in my sample sheet as columns. And so we're saying take the rows and leave them all the same in counts, but only take the columns from sample ID in sample sheet, which is the same. Sample ID is the same as the column names in there. So this way, if you accidentally downloaded more data, you're only going to get the things that came from your sample sheet, which we made in code, so it's 100% reproducible. Okay, so now we've subsetted our counts just to the samples. Let's make sure that all the call names, this is a true false statement here. So call names of counts, the column names in counts is the same as the column names in sample ID. And so if we just do call names counts, we see the name of our samples. And if we see sample sheet sample ID, we see the samples, and that's probably going to evaluate to true. And the answer is yes. So everything is organized. This is worth doing every time. If DE-seq and your sample sheet are off, then conditions could be compared wrong. And so that is just the way it goes. And it's worth doing every time. Okay, so now what we can see is sample sheet, sample name is the actual type of RNA it is. And we're going to make that the call names of counts, which is currently our sample name. And so we're going to now have the sample name and the type of RNA merged together into our counts matrix here. And so, yeah, so we have our counts object here, which has the type of RNA, the gene name, and the quantification. So that's all that we would need. And now we could do DE-seq on different of these comparisons and conditions. And what we're going to do first, though, is use DE-seq to get out normalized counts. So we're still working in count space here. We are going to then get them ready to go into DE-seq. Okay, so first thing we want to do is round our counts. We can see that these are big numbers, and DE-seq would prefer them to just be rounded integers. So we're going to round the numbers, and we can see here that they're now round numbers. And then we are going to take out any of the rows that don't have any values, so genes that are not expressed at all. And any of these samples are not needed and can sort of make the model DE-seq is going to run a bit less accurate. And so we can write that out. Here is our counts matrix because we just did a bunch of work. Now we can just load it in moving forward. So often when you're doing this more more routinely in the lab, this stuff is just, you just do it once, save it, and then start having fun looking at questions. Okay, so it's important to factor our sample sheet. So if we look here, we can look in this column, we see every column right now is CHR or character. I hope that's not too confusing with chromosome, but that means character here. And what we need is condition in our sample sheet is the type of RNA we have. So if we want to compare total RNA to insoluble, this is the column that would specify that. But it has to be a factor. And so a factor we used before to count replicates. And basically what it's going to say is, I'm going to take this name and make it a special meta tag that it's a factor that I can then take that name and look for other examples of that name and push them forward. Hopefully it'll get more intuitive as we do it, but really this is just going to change our condition column into a factor. So now we can see our condition is a factor with 5 levels only. So we have 10 names in there for replicate 1 and replicate 2, but it now knows the unique name of those samples from what type they are. And then it'll know that if there's 2 or 3 or 4 to treat them as replicates. So it's kind of simple, but also a bit to maybe pause and go back and think about is now, even though our sample sheet has these 10 entries in condition, it knows there's 5 unique ones, and it can use those as a factor in DE-seq, where we can say compare 1 to 2, 1 to 3, etc., up to factor 5 in this data set. Okay, factors are important. So we have a counts matrix. That's just the raw counts, not rounded, and a sample sheet that is factored by the conditions we want to compare. Okay, so we might want to write that out. And then our next step after getting counts is to create sort of tell DE-seq, what do you want to compare? Where are the counts? It only needs 3 little things. But it is important here. I put a link to this website, which I think is really useful in saying, why is it important to transform my data before using it? And the short of it is that if you look here, the standard deviation is a function of abundance. And so you want to sort of even out the standard deviation in your data. And here's a good example they have of what it looks like. So this would be our raw counts here. And what we can see is there's a lot more variance at the lower the number of counts, the more variable our certainty is of those counts, basically, is one way to think of it. And this is comparing like sample 1 and sample 2. And so we can see that it's a bit more dispersed. And what RLog counts is what DE-seq will do is give us counts that are more normalized. So you can see it took that spray at the bottom and it's shrunk it where it said at each given mean, what is the standard deviation? And let's sort of normalize that across each bin. And there's also VSD counts, which we're not going to talk about, but is in this document here that I have a link for there. Okay, so this is really what we're going to run DE-seq. It is fast and it is very little code, but is a lot of setup, as we can see. But we are finally there. And so these are, that document also has the DE-seq functions in it. What are the main ones to use? That is also quite handy. And so this is just things to memorize or copy and paste from. But first we need to set up a matrix. And so we're going to make this object DDS for DE-seq dataset. And we're going to use the function DE-seq dataset from matrix, which is a long function name. And what it needs as parameters is count data. And so we're going to give it our filtered counts, which we filtered out the zeros and rounded the values. The column data is going to come from our sample sheet of what to compare. And by default here, it's going to compare everything to everything. And we want to do that because we want to get out the RLog values for all of these comparisons. So that we'll get to that in just a second. And then the design is based on the column condition in our sample sheet, which has been factored. And so what DESeq is going to do is take whatever the first factor is going to be the denominator, and it's going to make the numerator every other comparison. So that'll give you the log2 ratio of the first factor divided under as the denominator and the next factor 2 as the numerator, make that comparison and make every comparison to each of the factors. And so that's a lot of work, and it runs amazingly fast. Okay, so once we have this DDS set up, which is just basically where's the date, the counts, the sample sheet, so that I can find the condition column to do DESeq on. Okay, so we have our input for DESeq, this DDS object. It converted to integer mode. Even typically when I do convert our counts to integer from as a number, that will still happen. So if you see that, don't worry, that's normal. So then all we have to do now is run DESeq, which is going to run the R-log counts and the comparisons of differential expression between all the conditions in the factor group. And so if we run that, it's running. It'll take a second, but compared to what it's doing, it does not take very long at all, and it's very efficient. And so what we're going to do in the next class is compare nuclear to cytoplasmic, 2 conditions we're going to do next, and then multiple conditions after that. But for now, what we're really getting out is just R-log counts that we might want to use to make heat maps and other bits of information, which we'll go over. But we want to save all this stuff. So now we have our DDS has been transformed by DESeq, and it has just tons of things. This is one of the most complicated objects I've come across. So, but we can look in the documentation of DESeq. There's only a few things to remember: this matrix one, DESeq itself, and then R-log, which is going to go into DDS and run the R-log normalization, which is going to take those low abundance counts and sort of make them more realistic, so they don't influence our statistics. Okay, so we are running that, and it's now doing that for each sample. And we are now going to have an R-logs count. So we ran R-logs on there, on R-log counts, and we can see it's in this long format, and you can go through and see what information is in there. But we're going to use the function assay to retrieve those R-log counts and make it our R-log counts matrix, which now will have R-log counts for all of our samples. Again, we're just setting up here. We've gone from counts to filtering out all the zeros to rounding them, and now we're normalizing them across the levels of the counts so that the lower numbered ones don't have as much variance. Okay, so let's grab them with assay and make this R-log counts matrix. And we can see it is 40,000 rows, so there must be about 40,000 genes in there, and 10 columns, which are our samples there. And now those are the values of the read counts in R-log normalized space. So let's write that out individually in case we want it later. But that's the main goal for today, was to just sort of go from our next flow, our NF core output, to reading in the counts, to making our sample sheet, just some of the last bits of setup we're going to do. And now we are ready to run all of this in the next class and compare nuclear to cytoplasmic. And then after that, we'll compare total RNA to all the different other fractions. Those will be more of the common things you would do. But for now, I'm going to save my environment here so that we can load that again. So now I could just erase my environment, come back tomorrow, load this in, and look at that. We're right back to where we were. Never gets old. All right, with that, we're moving on to doing some differential expression, but I hope you can appreciate and take some time to go back over this and just see like what are the steps you do. Maybe take some notes. They're not that long, but there's some important considerations before actually running differential expression. All right, with that, thank you and be well.